And opposite industry, renewable energy, Hanwha Solution, CS Wind, and Shinseong ENG, and Unison, SGC Energy. And I added carbon reduction industry, secondary battery, like EcoPro VM, PowerLogics, Samsung SDA, and hydrogen, Sangha Frontend, and CCUS carbon project that is a small cap, but I studied include this company, Fusong, EcoBio, Unity. So total sum 3-2. And next, the result of event study regarding waste management portfolios, significantly negative impact. That means event window, that event day, 10 days ago and 10 days after. So we found negative 8.645%. That is a really significant impact. We found on market model and mean adjusted and market adjusted model, both of them, we found all negative impact. It's like utility portfolio. Utility portfolio, more than waste management, they show the negative result. -10, +10 event on market model, negative -12.696%. Oh, really? Okay. And next. And next. Next. So, I carbon emission to achieving a 40 reduction. EU and Germany, they have 33 years and 35 years. But South Korea and Japan, we have only 12 years and 60 years. So, it burden on industry. And annualizing carbon reduction rate, South Korea, the most high. And next. That's okay? Okay, thank you. Yeah. So we select the South Korea, some company, and Japan company. We found a similar result. Korea also show the negative result. Japanese also, they show the negative result. And next. South Korea and Japan's stock market view it as a high carbon emission industry. Waste management industry, as you know, we can reduction carbon emission and we can help climate change. But the stock investor, they consider this industry as a high carbon emission. They see the shift to a low carbon society as a cost and a risk. So policymakers and the waste management industry should work together to turn these risks into opportunities. Additionally, clear policy directions and support through green finance should be developed to help with these changes. So, the next. So I will expand the country to 7 countries. Now South Korea and Japan, but I will expand it to Thailand, US, Europe, Malaysia also. So if you are interested with my research, let's collaborate. I want. And I'm looking for the partner globally. So I want to research together and I want a project globally, especially international carbon reduction project. So we do carbon reduction project on host country, and we can get the carbon emission right, and then we can sell this right to the market. This is the profit business. It's different with the ODA, and this will be led by private sector. So can together. Please contact me. In touch with you. Thank you. Thank you very much.
Yeah, sorry about the time. Yeah, you have plenty of time. Yeah. So do you have any questions or comments?
We Korean, they pose carbon emission amount. That is a carbon emission right also. So we cannot consider carbon tax. Profit.
We have carbon reduction.
Yes, right. That is the different side.
Okay, I see.
Yeah, that is a good point. Carbon tax is a negative vehicle through by government. But carbon emission right, we can sell to the private, so to the market. That market operate by private investor. So this is different. Carbon tax is regulatory. The carbon market is non-regulated. That is a private market.
So our market is applicable for any country in the world.
Oh, that's also a good point. Almost the country, they have their own market. Korea we also have, and Europe is very developed. And non-complacent market exists also. That is a voluntary market that open to all. But compliance market only country regulate. Yeah.
Okay, thank you.
Okay, good.
So thank you very much for your presentation. And you mentioned your research about the highly carbon company, utility company. For example, KEPCO, KPE, KPS, like that. But I think those companies is indirect carbon emission company. It's the direct emission company for GenCos. So your research for your stock market investor. However, carbon emission is very important issue. So I feel my comment is for your research further, and you mentioned about what GenCos produce a carbon emission. It's the more important issue, I think.
Very good comment. I think you are the most professional about this.
GenCo.
you experience in KEPCO, yeah. So you are more expertise more than me. That is a good point. And KEPCO and their subsidiary, they are doing carbon reduction project a lot. They are main leading player in this carbon reduction project. But the stock investors, they consider the KEPCO as a high carbon industry because KEPCO, they have renewable energy, but fuel energy more than renewable. So I could not distinguish this, even though KEPCO, they have a lot of renewable energy and carbon reduction projects. I will study more about that. Okay, thank you very much.
Okay, so yeah, let's thank you, Professor. So we'll move to the more oral presentations. So for each presentation, it's about 15 minutes. So 12 minutes for the presentation and 3 minutes for the team. Okay, so let's work on Shunpei Nohara. Yeah. The type. This one. This one. Okay, the title is estimating work density to reduce manual operation and waste incineration plants.
Sorry, kau join ni tak? Saya boleh ingat virus tapi ni sebelum ni dia tuan kemas. Okay. Nanti ni petang ni. Apa boleh kau yang minta virus lah? Kau bisa kemas saya tolong. Boleh tanya. Okay, dia guna report. Itu virus. Saya dengan apa? Tarik tinggi. Kalau letak cik virus ni. Cik virus IT. Boleh tak saya tanya tu virus? Tak apa tanya. Saya dah tanya tu Faiz. Tak lupa lagi takut dia nampak dia. Virus saya tak ada transport. Sebab itu datang saya. Kata kau ada tersebut. Tak apa, saya baik lambat. So dia nak kena cari transport tu hari ni, tu petang. Siapa orang balik pukul 5 kan. So kau dah boleh tengok situ lah. Kau check out? Check out? Saya ada kamar barang dan tinggal check out. Saya tunggu sekali hasil. Okay. Nanti apa nanti dah termisi lah. Nanti saya kena check. Baru setengah 20 minit. Ini saya kau ditanya.
Okay, thank you for the Professor for the introduction. Hello everyone, I'm Nohara Shunpei from Canada Corporation in Japan. Today I will be talking about real-time estimation method of waste bank density and reduction of manual operation in using it in waste incineration plants. Next slide, please. Let me give you the background of our study. Please look at this figure. This is a simple schematic incinerator, stoker incinerator. The stoker incinerator automatically controls blade speed and combustion airflow rate and combustion air temperature. For control, sensor value and parameter are used as input. Since the parameter values cannot be directly measured by sensors, representative values are input. Next slide. However, more stable combustion is expected by estimating parameters in real time and adjusting these values based on changes in the waste. Among those parameters, we focused on bulk density refers to the weight per cubic meter of waste. Knowing the bulk density can help control waste throughput model. We aimed to develop the method to estimate the bulk density in real time and to reduce manual operation for parameter changes. That covers the introduction. Next slide, please. I'll explain that. This is the overview of the method. Estimated targets are lower heating value and bulk density. These are estimated by two methods, such as material balance method and heat balance method. We set 4 assumptions. Number A, combustible composition in waste consists of only hydrogen, carbon, and oxygen. B, rare or ammonia used for denox can be ignored. C. Air consists of only N2 and O2. D. Flue gas consists of only N2, O2, H2O, and CO2. Here is flowchart. First, input operation data from DCS. Next, move on to estimation step using numerical optimization. Here assume that the optimization parameters are waste throughput and leakage airflow rate, and calculate LHVA and LHVB. And repeat this assumption and calculation until the difference LHVA and LHVB becomes sufficiently small. So, once the LHVA is determined, we finally estimate the bulk density using the correlation between the LHV and bulk density and output them. This is calculated every minute. Next slide. I'll explain the details of the estimation. On material balance method, the flue gas composition, air ratio, theoretical air volume, and theoretical oxygen volume are calculated from the exhaled gas. From this, the waste composition is calculated in reverse. The calculated waste composition is input into Duron's formula to obtain LHV. On the heat balance method, heat input and output and heat output of the incinerator are calculated from the incineration related data. Then the LHV is determined so that the heat input and heat output are equal. That covers method. Next slide, please. I will explain the demonstration test using proposed method. We conducted the test at the Eco Park Shioya plant located in Tochigi Prefecture, Japan. Please refer to this table an overview of the plant. The plant incinerates 114 tons of waste per day and generates 1530 kilowatt of electricity. We compared the 62 days test period with the same 62 days reference period from the previous year. In this test, we automatically adjust the parameter settings using the estimated bulk density. Next slide, please. Then, I'll show you the result of this test. First, please look at this figure. This figure is the number of manual changes of parameter settings. As is clear from the figure, the number has been reduced by about 87%. As is evident from this result, proposed method was able to reduce the number of manual changes. Next slide, please. The results for bulk density and LHV data. Please look at this left figure. This figure is bulk density settings histogram. The vertical axis is setting frequency, and the horizontal axis is bulk density settings. Gray color is difference period. Green color is test period. As you can see from this, the variation was small compared to the difference. On the other hand, please look at the right figure. Right figure is LHV estimation result histogram. The vertical axis is estimation results frequency, and horizontal axis is LHV estimation results. As you can see from this, the mean and variation was similar to the difference. From these results, we can conclude that the operator settings were changed to large. By keeping the settings within an appropriate range, the number of manual changes has decreased. That covers demonstration test. Next slide, please. Now let me summarize my talk. The goal and results of this study were the following two. One, develop the method to estimate the bulk density in real time. This was achieved by combining two LHV estimation methods, such as material balance and heat balance. Two, reduce manual operation for parameters changes. This was achieved by 87% reduction in targets. As the next step, we are considering further improve operational stability and reducing manual operation by using LHV and waste composition, which are not used in this test. This concludes my presentation. Thank you for your attention.
Thank you for your nice presentation. So we are open for questions and comments. So do you have any questions?
Okay, thank you for your excellent presentation. Would you please tell me about the estimation of bulk density method? How do you check the bulk density or just estimate or did you measure some real density?
Here, real bulk density.
Yeah, how did you estimate the bulk density? Just the estimation only, or did you check
Estimation only, not real measured bulk density.
So what is the number? How is this estimate? How did you estimate this? How is the result of the base density? Do you have any real number?
Bulk density is 0.31 is more.
This is from the estimation.
Yes, estimation.
But you don't have a real.
I don't have real data, so cannot measure by sensors. So estimation only.
So maybe it will be better to check the real density, right? Maybe there's a difference in the real estimation.
Okay. Consider.
So any questions or comments? So my question is, so in real operations, so the bulk density or raw heating value changes a lot. So yeah, I'm just asking the question that it is changed a lot or it doesn't change a lot in real operation.
My opinion is not so change bulk density or LHV. Bulk density LHV more change is not control incinerator. Incineration is very standard.
Anyway, there is a manual operation, so you want to reduce the manual operations.
Yes, My opinion, I don't manual operation. I don't like.
Okay, so thank you, and for the next presentation. So the next speaker is Mamoru Nishimoto, and his title is Pilot Scale Demonstration Test of Pyrolysis and Gasification Reforming of Municipal Solid Waste using an indirectly heated fluid.
Good morning. My name is Mamoru Nishimoto. I am from Canadian Corporation of Japan. Canadian Corporation is older name is Setsuse. In this October, we changed the name. Today, I talk about pilot scale demonstration test of pilots and classification reforming of municipal solid waste using an indirectly heated tube. Next, please. First, background. In waste treatment, decarbonization and resource circulation is required. To achieve decarbonization and resource circulation, we have developed pilots and classification reforming system for waste. And we demonstrate, verify the function of this system by pilot scale test. This system can treat waste which difficult to sort. For example, finished solid waste and textile, plastic. And next is our system. Main equipment is rotary kiln. And this rotary kiln, under high temperature, without oxygen, convert combustible material in the waste to combustible gas. The gas is mainly syngas, hydrogen, and carbon monoxide. That gas can be used for power generation, fuel for heat, and raw chemical materials for recycled materials. For example, PET bottle and shirts. Next, please. I talk about the characteristic of the kiln. This is small model of the kiln. This kiln is indirectly heated rotary kiln. This is indirectly, so heat from outside to inside. So we can achieve without oxygen. And unique industrial structure. This kiln consists of mainly two parts: pyrolysis part and gasification reforming part. At pyrolysis part, waste is decomposed to combustible gas, tar, char, and incombustible materials. At gasification reforming part, tar steam reaction is caused. So tar is converted combustible gas. And circulating media material is included in the kiln. Circulating media material is char and incombustible material from waste. This is for process. At pyrolysis part, this circulating media materials contribute for stable treatment. If waste property change, for example, water, a large of heated circulating media material, it becomes a big heat capacity. So it prevents temperature big drop. At gasification part, char is catalyst for tar steam reaction through tar steam tar contact. Okay, next please. I talk about pilot scale demonstration test. This project is commissioned project, Ministry of Environment, Government of Japan. The location is Osaka City. System is our developed pilots and classification reforming system. Waste is municipal solid waste, actually collected in Osaka City every day. Plant capacity is 70 kilograms per hour. It's 1.7 ton per day. Continuous feeding. Operation period is from March 2022 to October 2023. This picture is overview pilot scale plant. The table shows waste characteristics. Moisture is 40%, combustible is 54%, ash is 6%, and lower heating value is 10.9 megajoule per kilogram. As shown, the table, waste property change from minimum to max. So, change property, it is hard to predict. Next, please. I talk about process flow of pilot scale demonstration test. Main equipment is rotary kiln and gas purification system and heat gas generator. First, crushed MSW is fed to the kiln, and at pilot spot under 500 degrees, waste is decomposed to combustible gas, tar, char, and incombustible material. And at the gasification reform part, at 800 degrees, tar char steam reaction is caused. The gas after kiln consists of harmful substance for gas engine. So after the kiln, gas purification system cleans tar, acid gas, and soot in the gas. The cleaned gas is used in gas engine generator and heat gas generator. And temperature of the kiln is controlled by indirectly heated gas generating heat gas generator. Next, please. Next, I talk about stable treatment of the kiln. First, let me talk about left graph. This is trend operation trend data. Blue line is the amount of MSW fed, and orange line is internal temperature of the kiln. Target of 73 kilogram per hour, and temperature is 830 degrees. As shown in this graph, at 5 o'clock, internal temperature of the kiln start to be lower. This is because waste property change, so the amount of waste increasing. In this case, we adjusted the amount of MSW and indirectly heat gas. By this adjustment, temperature change could be reduced and become near set value 830 degrees. Next, I talk about right graph. This is gas composition trend data. Shows gas concentration volume percent. Blue line is hydrogen. Orange line is carbon dioxide, and gray line methane, and red is carbon monoxide. We focus two gas analysis. red and green first, second. In right graph, first gas analysis, the amount of FSW is 70 kg per hour. Second gas analysis, the amount of is 80 kg per hour. And right graph, both of the amount of FSW is different first and second, but there's no significant difference in gas concentration. In this slide, the conclusion of this slide, we can also the amount of MSW change, but little change in temperature of the kiln and gas composition. Next, please. Yes, this one. Next, I talk about property of the generator gas and gas utilization in demonstration case. The table shows properties of the generator gas in the system. First, cold gas efficiency. Cold gas efficiency means the percentage from waste energy converted to gas energy. Cold gas efficiency was 77%. And main gas was syngas, hydrogen 30%, and carbon dioxide, carbon monoxide 10%, and methane is 14%. The gas was used in gas engine generator in demonstration case. The picture is lightning by electrically generated from the gas engine generator in demonstration case. Next, please. Finally, conclusion. Achievement number one, the stable treatment of events was achieved. Two, the generator gas was used was mainly syngas and used in gas engine. Number three, operation achievement. The total of treatment time was 170.7 tons. The longest continuous operation period was 45 days. The continuous operation was 30 days, 3 times. As a result, this pilot test demonstrated the effectiveness of the pilot and gasification reforming system. That's all my presentation. Thank you.
Thank you for the nice presentation. So, do you have any questions or comments?
Thank you. Thank you for the good presentation. And I'm a little bit curious about the mix of the MSW, like what kind of materials in the MSW, like the plastic, how much percent of plastic and how much percent of some like textile?
In demonstration test. We analyze waste property sometimes, and the average is plastic is wet base 30%, and other is biomass.
There's a bio.
Yes, actually waste, for example, food and wood, like that. Plastic is 30%.
Let me ask you about some energy balance.
Yes, right.
So it's very important thing
Yes.
is you should enough resource from external resource.
Yes.
So you think it's enough for self resource?
Okay, please back to slide. One more. Yes, this one. Actually, in demonstration, we use fuel from outside for heat gas generator. We calculated by our result. We calculate we can operate without no outside fuel, and we can use gas engine generator. But this is in calculation, and we calculate for scale-up plant. But in calculation, we can achieve no outside fuel.
How about your pilot test?
Pilot?
Yeah. Did you supply any energy from outside in your pilot test?
Actually, this pilot test plan, we have already stopped, so we cannot test anymore. Sorry.
Pilot test is for the engine generator.
Yes.
So did you supply any other auxiliary fuel for the
Gas engine.
gas engine generator?
Yes. First,
Thank you very much.
so it is hard to control temperature of the fuel. Next, because of tar. But we try to some operation method, tar control. So we can achieve finally 45 days.
Okay, so the next speaker is from now. The title is Classification of IDF and Charcoal for Green Electricity Production.
I work at the Waste Incineration Research Center in Kingwood University of Technology, North Bangkok. On behalf of my team, I would like to present the investigation of coal gasification of reclaimed RDF and charcoal for green electricity production. Here is my presentation today. First of all, conclusion. Already know the rapid urbanization and globalization result in the increase in municipal solid waste generated annually. It was reported that in 2022, the amount of waste is generated approximately 2.1 billion tons annually. And the United Nations was predicted that the amount of municipal solid waste will increase to 3.4 to 3.8 billion tons in 2050. And the most generated MSW was globally disposed by open dumps and landfill, as you can see from this picture. Unspecified landfill of about 25% and open dump 33%. And the situation in Thailand is almost the same of the worldwide. And if you can see, landfill and open dump is unsustainable technology because there is no energy recovery from combustible material, and also especially for some country with limited space, there are maybe in the near future no land available for landfill. So we have the idea of to reclaim the old waste from landfill to be used as fuel because of there are, if you can see, this is the physical composition of old waste from Thailand. And from our research, we found that there are more than 50% of combustible material. But the disadvantage or the drawback of using old waste is directly used is because of the soil-like material resulting from the degradable of food waste or kitchen waste. And also, if you use it directly, the old waste is non-uniform. Therefore, it's come the idea of to make the uniform always as the RDF diffuse derived fuel and then upgrading the fuel properties by torrefaction process. And then the torrefied RDF is used as the fuel, the feedstock for gasification process, and producer gas can be further used as supplementary fuel for electrical production. The main objective of this study is to upgrade the RDF property through the gasification process and use the reclaimed landfill RDF as substitute to fossil fuel for green electricity production. Here is the feedstock preparation. We use the HDPE as the representative of plastic waste, and we use paper mixed together. From the previous laboratory scale experiment, we found that the ratio of 1:1 of plastic waste and paper is optimal ratio, and this study focuses on experimental tests in the small pilot scale. Therefore, we use the 15 kilogram per hour screw dry pressing machine in order to produce RDF, and the RDF produced from this machine has the diameter of 4.5 centimeter and the length of 9 to 10 centimeter. During the pressing, we heat it up to 100 to 120 degrees Celsius in order to melt some plastic waste in order to form the cylindrical cylinder. And after this, we call this the raw RDF, which has the density of about 550 to 600 kilogram per cubic meter. And then we use the 30 kilogram per hour torrefaction oven at the torrefaction temperature of 250 degrees Celsius for 30 minutes to produce the torrefied RDF. And this is the gasification process with diesel engine generator. Number one is the Dow gasifier, and you can see the real picture from this map. And number two is the gas cleaning process, and we have a sand filter in order to filter the tar contaminated in the producer gas before we using the producer gas as the supplementary to diesel fuel in the diesel engine generator, and we connected to electrical load of about 15 kilowatt. Here is the analysis. We focuses on the diesel replacement rate, feedstock consumption per 1 unit electricity production, and also the overall efficiency of the plant. In the experimental procedure, we run 9 tests, and RDF number 1 and number 1 to number 3 is we run the different amount of RDF and different amount of charcoal. Why we have to put charcoal in it? Because if you can see, it is a Dow gasifier, and if you put only plastic without, I put charcoal because I would like to increase the fixed carbon, because the plastic has the very high volatile matter, and if you put it into the gasifier, plastic can be melted and accumulate at the grade of the gasifier, and the producer gas cannot flow out, and the pressure inside can be increased. Therefore, I put the charcoal in order to increase the fixed carbon. And we would like number 1 to number 3, we would like to find the maximum amount of RDF and minimum charcoal that we can use, and at the air ratio of 4.3. The air ratios mean the actual air input divided into theoretical air input to the gasifier, to theoretical air input for complete combustion. And number 4 to number 8, we use also the in order to find the optimum air ratio with the highest efficiency. And number 9, we would like to compare the experimental between torrefied torrefied RDF and raw RDF, and we compare at the worst air ratio from lung number 4 to number 8. The results and discussion after torrefaction process, the carbon content and hydrogen content is a little bit increasing, but oxygen and choline decreases. And if you compare the lower heating value and high heating value, we can find that the torrefied RDF has the larger heating value than raw RDF. And for the result of gasification process, we can see that from number 1 to number 3, the least diesel at the RDF amount of 20 kilogram RDF and 10 kilogram charcoal can achieve the highest distillate displacement rate of 76.5%. Therefore, we use this amount for the next 4 experiment set. Therefore, and for the number 4 to number 8, we vary the air ratio from 0.2 to 0.4, and we can find that at the air ratio of 0.3, the diesel replacement rate is maximum, and also the overall efficiency of the plant is maximum, whereas the feedstock consumption per unit electricity production is the minimum value. And for run number 9 with raw RDF, we compare the average, the worst case of air ratio, and we found that for the violet here, the worst air ratio is 0.2, provide the higher diesel replacement rate and higher overall thermal efficiency than raw RDF. And if you see the feedstock consumption rate, you can see that if you use raw RDF, you need 1 kilogram of feedstock for 1 unit electricity production. By biomass, you use 0.87 kilogram. The conclusion of my presentation today is all MSW from reclaimed landfill has the high potential to be used as green energy resources for electricity production. The quality of reclaimed landfill RDF can be upgraded through the gasification process, by which the heating value of RDF increases. And from this study, the optimum operating condition for electricity production for torrefied reclaimed landfill is the charcoal ratio. The torrefied RDF and charcoal ratio is 2 to 1 by weight, and the air ratio of 0.3, which can achieve the maximum diesel replacement rate of 84%, maximum overall thermal efficiency of 15%, and the minimum feedstock consumption rate of 0.73 kilogram feedstock per kilowatt hour of electricity. Thank you very much for your attention.
Thank you very much for your presentation. So, do you have any questions or comments?
During your qualification process of your, what is the exhaust gas of the torrefied gas?
We use torrefied gas back to heat.
Heat again?
Yes, back to
No
heat.
exhaust gas.
Yes.
And then I have a question more. Before and after your qualification process, did you compare the energy before qualification and qualification materials?
The energy of what?
Compare. During your qualification process, you need some energy,
Yes.
input energy, and the final product energy. Did you compare it?
Yes, the You means the initial and final energy of the MSW, right? Yes, because the heating value is increased.
Yeah, what percent is consumed
Uh,
for making purification process?
You means energy consumption. I do not concern at the energy consumption at the moment because I also use the producer gas in order to it as the fuel for energy source in the torrefaction process.
I have a question. Okay. And any other questions or comments?
Good presentation, and your process is very good. I wonder, how about the cost benefit side? Is it cost effective? What do you think about that? No? Not yet? Have you conducted the economic analysis for your process?
I do the economic analysis, but I cannot remember the value
Number.
of it. Maybe I will send you later.
Okay.
I have to look into my report.
Okay, okay. Good.
Maybe many people think that you added the purification process and then you increase the economic benefit. Yeah. So maybe you need to compare
Thank
both
you.
cases. Thank you for your presentations. Okay, now to the next presentation. The presenter is Ryoka Mitsui, and the title is Ryoka. Yeah. The title is Reforming Pyrolysis Products toward Highly Efficient Energy and Resource Recovery from Sludge.
Hello everyone, my name is Ryoka Mitsui from Kyoto University. I would like to sludge. This is an introduction to my research. Sweet sludge has high energy potential. The total energy content of oven fodder is about 12 billion kilowatt-hour. However, the energy conversion ratio in 2022 fiscal year it was about 26%. So we focused on the gasification that contributes to carbon neutrality. The technology meets the social needs for high efficiency power generation and syngas production. The main products of the technology was tar and gas. Tar must be removed because tar causes plugging filters and pipes in actual plants, and tar contains a lot of energy. So catalytic steam reforming is effective in decreasing tar and increasing gases. Tar is oily condensable substances, and tertiary tar is our main product because our experiments are conducted at above 800 degrees Celsius, and tertiary tar contains aromatic compounds and polycyclic aromatic hydrocarbons. Tar cracking mechanism varies with each solid medium. Silica sand is an inert medium. In olivine, reduced metallic iron on the olivine surface cleaves the bond of carbon and carbon hydrogen, and the steam gasification and reforming of the carbonaceous solid deposition. In CaO, the CaO active site absorbs molecules H2O and CO2, and the basic site promotes dehydrogenation, dealkylation, and opening ring of tar molecules such as benzene. There have been many studies of catalytic steam reforming using toluene as modern tar and using sweet sludge in a fluidized bed. So our goal is to establish our highly efficient hydrogen and syngas recovery system toward more practical use, utilizing these previous work. So we reformed actual tower from Swiss was using our two-stage vertical fixed bed and used three media, silica sand, olivine, and CaO. And we quantified the maximum free-forming potential and compared actual tower. This table shows operating conditions and analysis methods. In actual tower experiment, pyrolysis temperature was 800 degrees Celsius, and reforming temperature in both experiments, reforming temperature was for 800, 850, and 900 degrees Celsius. We investigated carbon amount and gas composition, and we identified tower components. This figure shows experimental setup. Figure A is the setup for Tolen experiment, and the figure B is for actual tower. The actual tower was obtained by granulating the undigested dried sweat sludge into cylinders of about 5 mm and feeding 12 grains every 2.5 minutes. I'm talking about result and discussion. This figure shows carbon distribution of the Tolen experiment. The total amount of Tolen and benzene at each temperature, the amount are same in silica sand and olivine, while in CaO the amount was the smallest. And increasing temperature, the amount was decreasing, and the amount of Tolen was decreasing mainly in silica sand and olivine. The amount of benzene is larger in olivine than silica sand. The three separate conditions in three conditions are the amount of Tolen was less than 1%. And at each temperature, the carbon and solid media was the largest in silica sand. And increasing temperature, the amount of carbon in silica sand is larger, increasing. And the amount of gas carbon is the largest in CaO, and increasing temperature, the gas carbon was increasing. This figure shows gas composition of the Tolen experiment, and the production of CO and CO2 is larger in olivine than silica sand. It suggests that olivine promotes this dehydrogenation and water gas shift reaction, and CaO promotes water steam reforming reaction. So syngas volume is in ascending order: silica sand, olivine, and CaO. This figure shows the carbon distribution of actual tower, and the amount of Tolen was detected almost zero, and the amount of benzene was no significant trend compared to reforming. But at 900 degrees Celsius, this CaO. The is the largest in CaO, and olivine, in olivine and CaO condition, the gas carbon is largest in 850 degrees Celsius. This figure shows gas composition of actual tower. In olivine, and gas composition is same trend as gas carbon, but CaO was not same trend as gas carbon. So syngas volume at 800 degrees Celsius was the same as CaO and olivine, but at 900 degrees Celsius, the largest in CaO. This table shows the number of tower compounds identified by GCMS. PAH's mechanism was reported reported that benzene and acetylene are pioneer for PAHs, and PAHs transform into coke. In silica sand and olivine condition, some PAHs are detected. So, but the carbon amount of in solid media is larger in silica sand than olivine in Torrent experiment. So it suggests that olivine promotes steam reforming reaction of the carbonaceous solid deposition. And in CaO and in a Torrent experiment at 850 degrees Celsius and 900 degrees Celsius, no PAHs are detected. And in actual tower experiment, 900 degrees Celsius, the small PAHs are detected among solid media. It suggests CO promotes cleavage of aromatic double bonds of carbon. Conclusion. In Torrent experiment, olivine converts Torrent to benzene and CaO converts Torrent and benzene to gas. In actual tower experiment, almost no Torrent was observed and CaO converts benzene to gas. So syngas volume was 17.9 normal liter per mole carbon in CaO and olivine at 850 degrees Celsius. And syngas at 900 degrees Celsius was 21.0 in CaO and 16.7 in olivine. In future prospects, we will optimize various parameters for practical use of this technology, such as catalytic amount, steadiness time, and design of reactor, operating conditions, etc. Thank you for kind attention.
Yeah, a nice presentation. So, do you have any questions or comments?
Thank you for your presentation. I have one quick question. Is about like how do you like use the sand and the olivine and this CaO, like do you uniform their diameter or like you just mix them with the raw material together or you just separate them?
We inform the height of the solid media. So the diameter is different little, but we investigated the olivine small diameter experiment, but the result is not different olivine's diameter. Okay.
Okay, any other questions or comments? Okay, so,
Thank you for next presentation. So actually, I have quick question. Did you try to compare the energy and cost analysis in your study? Since in your research you use catalyst, and then catalyst is I think quite costly, right? So did you try to compare with the other technology, and then maybe they also do in the same area?
Compare other technology.
Yes. Maybe in the future you want to compare with other technology or sustainability.
No, I didn't compare as technology, but we focused on solid media or silica sand, olivine, and CaO, and it's not expensive catalyst. Yes.
Okay, no problem. I think I mean the performance. Maybe in the future you can compare the technology performance, maybe you can compare with the plasma or the other technology, since in here you use the, I don't know what kind of technology you use for this heating, for the combustion.
So you mean to heat it up the catalytic reactor?
Yes, catalytic reactor, right?
Okay, so maybe yeah, in a view of energy, maybe you need to heat up the catalyst reactor. So maybe it is not economically feasible. Maybe what he mentioned. So yeah. Okay.
Thank you.
Okay, so any other questions? Okay, then thank you.
Thank you.
Okay, so there is no more Roman or yeah. Okay, so we finish this session suddenly because of our reasons. So we have to announce the best paper of this, best presenter of this session is Ryuka Misi. Yeah, give by email. Okay. So after lunch, we will be in 2:10 for the closing ceremony of i-CIPEC. Okay, thank you for your participation.
수고하셨습니다. 전문가 앞에서.
아니 그게 아니라 이제 아마 그 스톡 인베스터 때문에